If you ask right now how long it would take us to reach Mars, the answer might sound simple. But the truth is that nothing about traveling to the red planet is as straightforward as it seems. The distance between Earth and Mars is constantly changing. The route we follow isn't a straight line, and rocket speed is far from the only factor that determines this journey. Today, you'll understand exactly why this trip takes so long and what the real time is for a mission to reach Earth's most famous neighbor. To start, we need to make something clear. Mars is not sitting in space like a destination waiting for us to arrive. It isn't a fixed point marked on some cosmic map. Both Earth and Mars are constantly moving, constantly changing position, and constantly shifting the distance between them. And because of that, the journey to Mars is as much about timing and precision as it is about distance. In fact, the moment you try to simplify the trip by imagining a straight line or assuming a constant distance, you step away from how space actually works. When people ask why we don't just go when Mars is closest, they imagine something like boarding a plane to a nearby city. But space travel doesn't work like aviation. There is no air, no roads, no simple direction to point toward. Instead, spacecraft follow the gravitational curves of the solar system, moving along orbital pathways that must be calculated down to the smallest detail. One mistake, one misalignment, and the spacecraft ends up arriving at a point in space where Mars used to be, not where it actually is. This is why reaching Mars isn't a matter of raw power or building a faster rocket. It's a matter of understanding the solar system as a constantly shifting environment where everything is in motion. If you imagine Earth and Mars racing around the Sun like two runners on different lanes of a track, you begin to see the real problem. They're never in the same place twice. The track keeps moving, the race never stops, and you can't simply run straight across the field to meet the other runner. You have to time the moment perfectly so that your path intersects theirs at the exact point where they will be, not where they are. And this is only the beginning. To truly understand the length of a Mars journey, we have to explore not only changing distances, but orbital speeds, launch windows, fuel limits, and the physics that force spacecraft to take long, slow, energy-efficient paths. The complexity begins here, with motion, timing, and a universe that never stands still. To understand why reaching Mars takes months instead of days, we first need to understand the relationship between our two planets. Earth and Mars are not stationary points in space. They're passengers in a massive cosmic dance, each moving at different speeds along different orbital paths around the Sun. And this movement creates one of the biggest challenges in interplanetary travel. The distance between the two worlds is constantly changing, often in dramatic ways. Earth orbits the Sun once every 365 days, at an average speed of about 107,000 km/h. Mars, being farther from the Sun, moves more slowly, about 86,000 km/h, and takes roughly 687 days to complete one orbit. This difference in speed means that Earth is continuously catching up to, passing, and then moving away from Mars in a repeating cycle. It's never static. It's never predictable at a glance. The distance between the planets is always in flux. At their farthest, when Earth and Mars end up on opposite sides of the Sun, the distance can soar beyond 400 million kilometers. But during a close approach, when both happen to align on the same side, that distance shrinks to about 54 million kilometers. That's more than a seven-fold difference. And this variation is exactly why travel time is not a single fixed number. Depending on when you launch, your spacecraft could face a journey that is comparatively manageable, or one that becomes nearly impossible with current technology. But even that closest point of 54 million kilometers doesn't mean a speedy trip. Many people imagine that when Mars comes near, we simply fire a rocket straight at it. But if we did that, by the time our spacecraft arrived at the location where Mars was, the planet would have already moved millions of kilometers ahead along its orbit. Space travel isn't about where things are, it's about where they're going to be. Think of trying to throw a ball at a moving train. You don't aim at the car you see in front of you, you aim where that car will be by the time the ball reaches it. Now scale that idea up from a train to an entire planet, and from a few seconds of timing to months of celestial choreography. That is the real challenge. This is why engineers treat planetary motion as the foundation of any Mars mission. To reach the red planet, we must design a path that intersects with its future position while accounting for hundreds of millions of kilometers of movement. And that path is not straight, simple, or short. It is dictated by orbital physics that force us to take longer, curved, highly calculated routes that prioritize efficiency over speed, precision over power, and timing over raw distance. If you imagine a spacecraft heading toward Mars, you might picture it accelerating out of Earth's atmosphere and then steering directly toward the red planet like an airplane following a flight path. But space doesn't work that way. There are no straight lines, no fixed roads, and no shortcuts. Everything in space moves along curved trajectories governed by gravity. And because of that, the most efficient and reliable route from Earth to Mars is something called a Hohmann transfer orbit, a slow, elegant, elongated ellipse that takes a spacecraft from one orbit around the Sun to another. Here's the key idea. When we launch a spacecraft, we aren't just shooting it across space. We're giving it a new orbit around the Sun, one that gradually stretches outward until it intersects the orbit of Mars. Instead of chasing the planet, we aim the spacecraft toward a point in space where Mars will be months later. This is the same principle behind leading a target, except now the target is a world moving at 86,000 kilometers per hour. The Hohmann transfer works like this. Earth orbits closer to the Sun, Mars orbits farther. We accelerate the spacecraft just enough to leave Earth's orbit and enter a larger elliptical path that reaches outward to Mars orbit. The spacecraft then coasts, carried by momentum and the Sun's gravity, all the way to the intersection point. It's a smooth, predictable trajectory that uses the least amount of fuel possible. And yes, least fuel possible is crucial. In space travel, fuel is everything. Every extra kilogram requires more thrust. More thrust requires more fuel. More fuel makes the spacecraft heavier, which once again demands more thrust. This creates a chain reaction that becomes unsustainable very quickly. That's why engineers prioritize efficiency. A perfectly straight, direct line toward Mars would require an extraordinary amount of fuel, far more than any current rocket could carry. To understand why the Hohmann transfer is so important, consider its history. Almost every successful Mars mission has used it. Mariner 4 in 1964, Mariner 6 in 1969, Viking, Pathfinder, Spirit, Opportunity, Curiosity, Perseverance. All of these spacecraft followed some form of this elliptical journey. Despite being slow compared to fantasy rocket launches, the Hohmann transfer is reliable, predictable, and energy efficient. But there's another catch. Even with the perfect trajectory, timing must be flawless. You must launch at a moment when Earth's position, Mars' future location, and your spacecraft's path align precisely. And that perfect moment appears less often than you might expect, which leads directly into the next challenge. Even if we choose the perfect trajectory and understand how to follow an efficient elliptical path around the Sun, there is still one fundamental limitation that dictates every Mars mission. We can only launch at the right moment. In spaceflight, that perfect moment is known as the launch window. And when it comes to traveling from Earth to Mars, this window is incredibly rare. It opens roughly once every 26 months, meaning we get just one realistic opportunity every 2 years to begin the journey. Why so limited? Because Earth and Mars are constantly moving along their orbits at different speeds. For a Hohmann transfer to work, Earth must be in the exact right place to start the elliptical path, and Mars must be at the precise future location where the spacecraft will arrive after months of coasting. If either planet is even slightly out of alignment, the spacecraft could pass behind Mars by millions of kilometers, or shoot far ahead, missing the planet entirely. There are no second chances in space. The timing must be exact to the day, sometimes even to the minute. Imagine trying to jump onto a carousel horse that is spinning around a circle. If you jump too early or too late, you miss it. Now imagine that carousel spinning at tens of thousands of kilometers per hour, and the horse being a planet. That is the scale of precision engineers must handle, and this is where fuel becomes another critical limitation. You might think we could simply launch more often if we had a more powerful rocket, but in reality, going outside the optimal launch window would require enormous amounts of additional fuel, far more than current rockets can carry. Every bit of extra speed demands exponentially more fuel, and that spirals into a problem. More fuel means a heavier spacecraft, which requires even more thrust to lift off, which once again requires even more fuel. The cycle becomes impossible to sustain. This is why nearly every Mars mission ever launched has done so during the aligned 26-month window. It's not a preference, it's a necessity. The solar system's mechanics dictate the timing, and no human technology today can change that. Because of this strict alignment and fuel efficiency requirement, travel times remain remarkably consistent. Missions almost always take between 6 and 9 months, regardless of the rocket used. The limiting factor isn't speed, it's energy. And as long as we use chemical rockets and energy-efficient transfers, the journey will always be a months-long commitment. These limitations raise an exciting question. What would it take to dramatically shorten the travel time? What kind of propulsion, engineering, or innovation could turn a 7-month journey into something far faster? To answer that, we must look toward the future. With everything we've explored so far, the shifting distance between planets, the curved paths dictated by gravity, the strict timing of launch windows, and the fuel limits of current rockets, it becomes clear why our journey to Mars consistently takes between 6 and 9 months. But this naturally leads to the next big question: can we ever make the trip faster? And more importantly, what new technologies could reshape the future of interplanetary travel? The good news is that engineers and scientists around the world are already working on solutions. While chemical rockets have served us for decades, pushing spacecraft out of Earth's gravitational well with tremendous power, they are no longer enough for the next era of exploration. To truly cut travel time, we must develop propulsion systems that offer more sustained acceleration, higher efficiency, and far greater energy density. One of the most promising technologies is nuclear thermal propulsion. Instead of burning chemical fuel, these engines heat hydrogen using a small nuclear reactor, then expel it at incredibly high velocities. The result is thrust far more efficient than anything we use today. NASA studies suggest nuclear thermal engines could reduce the travel time to Mars from 7 months down to around 3 or 4, nearly cutting the journey in half. Another emerging technology is nuclear electric propulsion, which uses a reactor not to produce thrust directly, but to power highly efficient ion engines. These engines produce smaller thrust, but can operate continuously for months, gradually building tremendous speed. Over long distances, ion propulsion can outperform chemical rockets by a wide margin, potentially allowing much faster interplanetary missions. There are also experimental ideas like plasma engines, solar sails, and even fusion propulsion, which, although still in early stages, promise speeds that could one day take humans to Mars in weeks rather than months. Fusion engines, for example, would harness the same process that powers stars, offering unmatched energy output with minimal fuel. While the technology remains theoretical, the possibility inspires a future where interplanetary travel becomes routine, efficient, and dramatically faster. But speed alone won't define the future. Safer spacecraft, radiation protection, artificial gravity, and autonomous navigation systems will all play crucial roles in transforming Mars missions from experimental journeys into sustainable operations. The day we reach Mars in a matter of weeks will signify far more than a technological milestone. It will represent a shift in what humanity believes is possible. And that brings us to the heart of the vision. Every advancement we make brings us one step closer to becoming a multi-planetary species, a species capable of crossing the gulf between worlds not as visitors, but as explorers with a future beyond Earth. With new propulsion systems, smarter engineering, and missions already being planned for the next decades, the age of faster Mars travel is approaching. And when that day arrives, the journey that once took months may become the opening chapter of a much larger story, one where humanity truly begins its life among the stars. As we stand at the edge of this new era, every discovery, every test engine, and every launch brings us closer to rewriting what's possible in space exploration. Mars is no longer a distant dream. It's becoming the next chapter of our story. If you want to follow this journey and explore the breakthroughs shaping our future beyond Earth, make sure to subscribe and stay connected. The universe is full of questions, and together, we're just getting started.